Log on, tune in, find out. Another good idea from Cambridge.
Who will speak to us about the Odd NilHecke algebra.
Thanks a lot.
Oh, he's from USC.
So usually I'm always reminding people I'm working with Kovanov on these things, but since I'm also working with one of his graduate students who'll be looking for a job soon, I should make a point of mentioning that I have some co-authors, joint with Michael Kovanov and Alex Ellis from Columbia. So what I want to talk about today is a new development in the sort of theory of categorified quantum groups. But to explain where this development comes from, I'd like to just take a step back and sort of explain again where my own perspective about categorified quantum groups, why I became interested in them. So my original interest in categorifying quantum groups was knot theory, and in particular there's a knot invariant called the Jones polynomial, which we're probably all at least somewhat familiar with. This is a knot invariant that's associated to the representation theory of quantum SL2. And this knot invariant was categorified by Kovanov to a homology theory associated to knots, where the sort of graded Euler characteristic recovers back the Jones polynomial. So when I originally became interested in this problem, this was sort of where the picture was at, and I sort of was most curious about what is the representation theoretic explanation of this, higher knot theory. Where is this stuff coming from? In particular, I thought there should be some sort of categorified quantum SL2, which explains why there's this categorification. So there should be some sort of categorified representation theory. Of course, that idea goes back to Igor Frankl, the fact that there should be some sort of categorification of SL2. And of course, Igor Frankl was motivated by geometric constructions of Lustig and Ginzburg. So that was where the story was at. But a lot of you know, if you've studied categorification very much, you know that categorification is often not unique. And in 2007, Ojvath, Rasmussen, and Szabo introduced a new categorification of the Jones polynomial. So we have Kovanov homology, and the graded Euler characteristic of this theory, decategorification, was the Jones polynomial. But then there was another theory, which they called odd Kovanov homology. And this also decategorifies to the Jones polynomial. So you might wonder, well, maybe these two theories are the same. In fact, these two theories are not the same. There's results of Shumakovich where you can find knots which are distinguished by odd Kovanov homology, which are not distinguished by Kovanov homology, and vice versa. So these are completely inequivalent theories which decategorify to the same thing. Now, one fact about this is that these do agree mod 2. So they're very similar in that they agree mod 2, but when you don't take that mod 2 reduction, they're actually quite different. So the sense in which this is odd Kovanov homology is if you go and you look at this actual construction of this knot invariant, Kovanov homology is based on the sort of symmetric algebra, whereas odd Kovanov homology is based on the exterior algebra. So now, if you're coming at this from a knot theorist, there's the question. There's two categorifications of something related to SL2, which are both decategorifying to the same thing. Where is the odd theory of categorified quantum groups? And that's what I want to talk about today. So in this talk, I'm going to just focus on SL2, and in particular the positive part of SL2. So the algebra which categorifies U plus for SL2 is called the NilHecke algebra, and this algebra is somehow fundamental in the theory of categorified quantum groups. So let me remind you a bit about that before I tell you what the odd NilHecke algebra is. So let's write NHA for the NilHecke algebra. This has generators x1 to xa and partial 1 up to partial a minus 1. Now, in my work with Kovanov, we like to think of this algebra sort of diagrammatically, where x sub I looks like some strands where we put a dot on the ith strand, and partial I looks like a crossing of the ith and I plus first strand. And it's sort of a generic crossing. We're not putting like braid or anything like that. The relations in this algebra can also be nicely diagrammatically encoded. So the x's commute with each other, which from an algebraic point of view is a very natural relation. And also this looks quite natural diagrammatically. It just says that if I have two dots at different heights, I can exchange the heights. And similarly, if my crossings and my dots are far enough away from each other, so I minus j is bigger than 1, then a crossing and a dot commute. And there can be a number of strands in between there. The idea is just this sort of commutativity. And normally when Michael and I are talking about these, we just say, we're considering diagrams up to planar isotopies, and we sort of ignore these relations. The sort of most interesting part of the NilHecke algebra is the relation which says partial I squared equals 0, which looks like this. You have a triple point relation which says, as we're all familiar with, I won't even write it, this holds. And the most interesting relation is the sort of the way in which the dots and the crossings interact. This is what I really think of as being the main SL2 relations, or the main NilHecke relations. And just to make sure my conventions are clear, I'm sort of reading from bottom to top. It goes crossing first, then dot minus equals the identity. And you also have another one where the dot's down here. So this algebra generated by these pictures modulo those relations is called the NilHecke algebra. And what's nice about this algebra is that it's very closely connected to a lot of fundamental objects in mathematics. So to see that, first note that the NilHecke algebra has a natural action on polynomials. So how does this action work? Well, xi just acts by multiplication, and partial I acts by divided difference operators. So in particular, partial I, so for some f in the polynomial ring, partial I of f is just take f, subtract off si of f, so just take the xi and xi plus 1 and interchange them, and divide by xi minus xi plus 1. So using this natural action on polynomials, it's possible to really get at the structure of the NilHecke algebra. In particular, you can see that, well, it's just a well-known fact that the polynomials in A variables is a free module, free lambda A, which is just the Sn invariants. So it's a free lambda A module of rank A factorial. And how do you see that? Well, I mean, you can just take a basis given by the Schubert polynomials, and then any polynomial in A variables can be written as some combination of symmetric functions times the Schubert polynomials. And again, one thing that's nice about these Schubert polynomials is that you can define them in terms of divided difference operators. So namely, just the Schubert polynomial SW in A variables is just partial W inverse W0 on X delta, where W0 is the longest word, and delta, X delta is just X1 to the A minus 1, Xa to the 0. And when I say partial of some word in the symmetric group, I just mean write this word in terms of elementary permutations, and then apply a partial I for each permutation that shows up. So like the longest word in S3, say S1, S2, S1, would just be apply partial 1, partial 2, partial 1. Okay, so using this fact, it's easy to see that this NilHecke algebra has a map into endomorphisms over lambda over the symmetric functions of Zx1 through Xa. So namely, every element in the NilHecke algebra gives me an endomorphism. It acts on polynomials by endomorphisms. But because of this fact that it's free of size A factorial, this is just looks like a big matrix of size A factorial with coefficients in the ring of symmetric functions. So the NilHecke algebra is really just this matrix algebra of size A factorial with coefficients in symmetric functions. And, well, at least it maps into there. What I wanted to tell you is that this is actually an isomorphism. And it's not so hard to see that. There's several proofs in the literature now, and I'm sure this fact is known to experts. But what does that tell me about the structure of the NilHecke algebra? Well, this implies there exists a unique graded indecomposable projective module for the NilHecke algebra. Let's call it PA. So if I look at the category of projective modules over the NilHecke algebra, this is the category which is supposed to categorify the positive part of SL2. What happens, we see that if I write NH for just the direct sum of all of these NilHecke algebras for all A, then what we see is that the Grothendieck of the sort of projective modules, graded projective modules, let's say finitely generated, graded projective modules. This turns out to be isomorphic to the integral version of the plus part for SL2. And the way you think about that is, well, what's going to correspond to e to the a in SL2? Well, this is just the projective module NHA as a NHA module, or I guess as an NH module. It's module. And where do divided powers come from? Well, that's just this unique indecomposable projective. So what's going on with this isomorphism is that this isomorphism categorifies the relation which says e divided power a is e to the a over quantum a factorial. So this is how divided powers are defined in quantum SL2, where a is q to the a minus q to the minus a over q minus q inverse, and this is just a times a minus 1, etc. So we're getting a categorification of this relation. How is that working? Well, the NilHecke algebra, which as a projective module we're thinking of as being e to the a, is isomorphic to a factorial copies of this unique indecomposable projective. So that relation, the main relation for SL2, is somehow encompassed in that isomorphism. And I wasn't really being careful with the gradings here, but if you keep track of the gradings of the Schubert polynomials, this is actually, as a graded ring, this is an isomorphism, where we have to sort of keep track of what's going on in these matrices. So this is the real reason why the NilHecke algebra plays such a key role in categorified quantum groups. Another explanation is that the NilHecke algebra is connected to cohomology of flag varieties, which I'll discuss in a little bit. And these, we all know there's like very natural actions of quantum groups on categories associated to cohomology rings and various things of flag varieties. So that's the NilHecke algebra and its relationship to categorified SL2. Now what I want to tell you is how to alter this story to get something which should be related to odd Kobanov homology. Is there any questions about that before I go on? Okay. So the odd NilHecke algebra. So it has the same generators. And the relations are very similar. And again, you should keep this idea in mind that in odd Kobanov homology, everything agrees mod 2. So everything that I write down on the board should be the same as the NilHecke algebra mod 2. So here's the first place where things are slightly more interesting. Remember how xi and xj commuted? Now we require that they anti-commute. And this is sort of motivated by the skew commutativity that shows up associated with the exterior algebra that shows up in odd Kobanov homology. This also shows up in Kovanov's categorification of GL11 based on the work of Lipschitz, Ajvest, and Thurston in Heger-Fleur theory. But in any case, diagrammatically, it's very simple to write down. We just require that these generators skew commute. We still require the main NilHecke relation. Again, everything has to agree mod 2. This triple point move still holds. And this relation gets modified in a very simple way. We just see that the minus becomes a plus. So this is a very innocuous change, but it turns out to have pretty significant implications. So this is the odd NilHecke algebra. I should mention that this algebra appears in recent work of Kang, Kashiwara, and Tsuchioka, where they were studying sort of different analogs of the KLR algebras, which were supposed to be related to Hecke-Clifford superalgebras in various affine types. We're, of course, arriving at this from a different perspective, but it's the same underlying algebra. Okay, so now what we'll do is we'll try and copy as much of this theory that worked for the NilHecke algebra with the odd NilHecke algebra and see how much of it goes over. So where the NilHecke algebra had a natural action on polynomial ring, the odd NilHecke algebra has a natural action on a skew polynomial ring. So if I take polynomials in x1 through xa, mod xi xj equals xj xi if I is not equal to j. So they skew commute, whoops, minus. Oh, I guess I should just say plus, like this. Mod that. So how does it work? Well, first, note SA acts on, I'm going to need a shorter name for this. Let's just call this P of A with a minus to indicate that it's sort of the skew analog of the polynomial ring. So SA acts on PA minus via an action where Sj on xi is minus xi plus 1 if j equals I. It's minus xi if j equals I plus 1, and it's just minus xj otherwise. So first I'm just, in the same way that on the ordinary polynomial ring there's a natural symmetric group action, on the skew polynomials there's a natural symmetric group action, but notice everything is getting a minus sign. Okay, so then partial I acts as follows. First, we're not going to have a nice formula like we had for the even case. Instead, we say that partial of 1 is 0, partial I of xi is 1, and partial I of xi plus 1 is 1. Now, in the even case, what you would have gotten is that partial I on xi was 1, but partial I on xi plus 1 was minus 1. So normally that would have been a plus 1 and a minus 1. And you could get at this, this definition that I gave you in terms of divided difference operators by starting with this and then just applying a Leibniz rule. So in the odd case, we don't have a closed formula like divided difference operator yet, but you can extend this definition by Leibniz rule and say that partial I on f times g is just partial I of f times g plus let Si act on f, and then apply partial I of g. So that's why I needed to tell you what this symmetric group action was. And the same formula holds in the even case where you have the usual symmetric group action on polynomials. So you might wonder, in the even case, when we saw that the NilHecke algebra was isomorphic to the matrix ring with coefficient symmetric functions, you might ask yourself, what's so key about symmetric functions in that statement? Is it the fact that these symmetric functions are the things which are invariant under the symmetric group action? And I claim that's not what was sort of fundamental about them. There's a different reason why symmetric functions show up, and this is because they're exactly the kernel and the image of the divided difference operators. So in the even case, symmetric functions, which happen to be the SA invariants, were also the intersection of the kernels of all divided difference operators, which were also the intersection of the images of all divided difference operators. If you're wondering where this is coming from, remember we had this relation which said crossing squared is 0. The reason that crossing squared is 0 is because first I'm mapping all polynomials onto symmetric polynomials. The kernel of all these divided difference operators is symmetric. sorry, I should be reading up. And say,
I was going to say it's
Yeah.
only symmetric in those variables.
yeah, right. It's only symmetric in I and I plus 1. And then if I apply this again, I'm applying it to something which is symmetric, and I get 0. So this is somehow the thing that's relevant about these symmetric functions. And again, the isomorphism between the NilHecke algebra and the matrix ring over symmetric functions comes by realizing the polynomial algebra as a free module over this thing of rank a factorial. So in the odd case, we can define a ring which I'll call lambda a minus, which is no longer related to the SA invariance on skew polynomials, but it is still, you can show the intersection of all the kernels of these divided difference operators that I've defined here and the images. So this is some ring which I'm going to claim is the odd analog of symmetric functions. First thing that we should note is that this ring is non-commutative. So let me tell you, you can do a little bit of work. You can show that this ring is spanned by things which look like elementary symmetric functions. So lambda a minus is spanned by what I'll call E1 up to EA with the degree of EJ. Depends on if we're calling our variables. We'll just say 2j. And relations, let's say EI, this part can be a little tedious, but I just want to write it down so that you can see what they look like. So if we were doing ordinary symmetric functions, these things would always commute, right? These are elementary symmetric functions, and they always commute with each other. In the even case, we're getting some slight differences depending on the indices here. And this is, again, just to sort of show you what these look like. You should observe that mod 2, this again agrees with symmetric functions. But otherwise is different. So here's one place where you can really see the difference. Normally when I commute E1 past some other E, they just commute. Now what's happening is I'm picking up this extra term where the index grows by some. So this is the ring of odd symmetric functions. This was derived in a different way by Kovanov and Ellis in a paper that was on the archive not too long ago. The starting point from that other derivation of the same non-commutative ring was there's a way of defining symmetric functions which is much like the way Lustig defines the quantum group U+. Namely, you start with this free algebra, and then you quotient by the radical of a bilinear form. So there's a way of defining symmetric functions by saying the symmetric functions are this free algebra modulo the radical of a certain bilinear form. Now you take that bilinear form, and you can find a Q analog, and define this Q analog of a bilinear form, and you get a Hopf algebra in that setting. And this has been studied by many people. But it turns out if you take a specialization of this bilinear form, it becomes degenerate. So taking Q equals 1, it's the bilinear form that corresponds to symmetric functions. Taking Q equals minus 1 is a specialization which gives you these defining relations. and this odd theory that we're going to talk about. So, by introducing odd analogs of Schubert polynomials, and again, what do I mean by this? I just mean take the exact same formula that you use to define the Schubert polynomial, namely this divided difference thing applied to x delta. Do the same thing in this odd case, and you can see that this polynomial ring is isomorphic, well, I guess I should say, is a free lambda a minus module of rank a factorial. Notice this ring, this is just like the other theory, except for now lambda a is non-commutative. And using this, we can show that the odd NilHecke ring, which I don't think I gave it a name, but I'll just start sticking minuses on everything to indicate odd. The odd NilHecke ring is isomorphic to matrices of size a factorial with coefficients in odd symmetric functions. And in particular, this ring NHA minus also categorifies U plus SL2. I should remark all of the combinatorics that you know and love for the symmetric group apply to this odd symmetric group. The odd symmetric functions. Namely, you can define analogs of elementary, you can define analogs of complete. They're going to satisfy a relationship that's very similar to the relationship between elementary and complete symmetric functions. You can define Schur polynomials. And again, this ring is spanned by, it has a basis given by odd Schur polynomials. And all of these nice relationships that you know and love for symmetric functions holds in this case, only everything is non-commutative. Is there any questions about this? Okay, so that's the odd analog of just the story for U+. What I want to talk about is some of the other exciting things that happen with the NilHecke algebra and compare with what's going on in this odd setting. And then is that related to the symmetric functions with for Q? I don't know. I haven't tried. Somehow, though, those Q, I think that's a really good idea. The point is, those other possible symmetric function rings that you have for generic Q, somehow they become most interesting when that form is degenerate. So the Q values where that form degenerates. So the -1 analog, you might imagine some other root of unity or some other thing where they get very exciting, and then there probably should be an analog of the NilHecke algebra associated to that Q, and probably everything goes over, but I haven't thought about that yet.
And when you write NHA minus categorifies U plus SL2, you mean that the direct sum over all A
yes.
projective modules and so on?
That's right, yeah. So take the sum over all A, take the categories of projective modules, and really the only observation, this ring is not terribly exciting. All we need is to have divided powers. And the fact that it's this matrix ring and it has a unique and decomposable means that if we treat that unique and decomposable as being the divided power, then the projective module for the identity here decomposes into A factorial copies. So that's really all I mean. So I want to talk for a minute about cyclotomic quotients of the NilHecke algebra. So these were defined by analogy with cyclotomic quotients of the affine Hecke algebra. We defined cyclotomic quotients of these NilHecke algebras and more general KLR algebras. And these are supposed to be connected to sorry. These are supposed to be connected to the representation theory of the corresponding quantum group. So cyclotomic quotients. So again, if you're not familiar with this, the idea is that the same way in which Arrighi's theorem holds for affine Hecke algebras, and that the affine Hecke algebra sort of is controlling, in some sense, categorifying irreducible representations of SLN, we're going to see a similar story where the cyclotomic quotients of these algebras also categorify the irreducibles. But since I'm doing SL2, it's not as exciting, but I think we'll see that it's still quite nice. So in the even case, if I take some highest weight for SL2, so some integer bigger than 0, and I define the cyclotomic quotient NHA lambda to be the NilHecke algebra modulo x1 to the lambda. So the way I think about this in terms of pictures is just saying if I have a lambda many dots on my first strand, that diagram is 0. So this is the cyclotomic relation, and if I define NH lambda to be the direct sum over all A, I guess I could just use N, of these cyclotomic quotient rings, one can show that the Grothendieck ring, the split Grothendieck ring of projective modules over this, is isomorphic to V lambda. The irreducible, and again, when I say isomorphic, I mean the sort of integral version of the representation, because the Grothendieck ring is a ZQQ inverse module. So these cyclotomic quotients categorify the irreducible representations. And there's a reason why this is true. The reason is because you can show that these cyclotomic quotient rings are Morita equivalent to cohomology rings of Grassmannians. So the cyclotomic quotient is isomorphic to the matrix ring of size A factorial with coefficients in the cohomology ring of the Grassmannian of A planes in big lambda weight space. So if you're wondering how that works, well, there's probably a bunch of ways of proving it. One way that I first proved this with, one way in which this was first proven was to just see what happens with x1. So this isomorphism between the NilHecke algebra and matrices over symmetric functions, you can write this down explicitly, like say where a generator, which elementary matrices come from which generators here. So you can write this isomorphism down completely explicitly. You look and see where does x1 go under this isomorphism. See what happens by taking x1 to the lambda power under this isomorphism. And you see that the relations that get imposed are exactly the relations which carve out the cohomology of the Grassmannian out of the ring of symmetric functions. So that's sort of the reason why this is working. And as a graded ring, this is a graded local ring, so it's going to have one indecomposable. So this just contributes to the Grothendieck, a one-dimensional term. So if I sum over all the A's going from 0 to lambda, I get a lambda plus one-dimensional vector space. So since each of these are this is the weight space in my irreducible SL2 representation. You should think of it like this, where, well, you have to sort of shift things to where this would be like GR 0 lambda, GR 2 lambda, etc. And you can actually define the E's and F's using different partial flag varieties, and this is an old story that's well known. So now the question is, what happens in the odd case? So in the odd case, we can define the Odd NilHecke algebra. I'm running out of places to put decorations here. So this is the cyclotomic quotient ring for the Odd NilHecke algebra as just quotienting by x1 to the lambda, just as before. And again, if you take exactly the same proof, just like sort of tracing things over, exactly the same proof is going to work to show that this ring NHA minus lambda is isomorphic to a matrix ring of size A factorial with coefficients in some ring which I'll denote as HA lambda. And I want to claim that this ring should be thought of as the odd cohomology of the Grassmannian. It's a non-commutative ring. So in what way is this odd cohomology like the ordinary cohomology? Well, for one, the Schur polynomials, I guess I should say the odd Schur polynomials, having at most A rows and lambda minus A columns restrict to a basis of this ring. So in the same way that if I start with the Schur polynomials,
What's your top generator in PA? You're applying the del i's to some top generator to get these Schur.
so Schur polynomials? Oh yeah, so it's the same thing. So Schur polynomial S lambda is defined as partial W0, where you actually have to choose an ordering here because things skew commute. You actually have to fix a choice of what you mean by the longest word because remember when we slide generators in this world, we pick up minus signs, so not all the longest words are the same. But this is partial W0 on X delta plus lambda. So this would look like partial W0 on x1 to the lambda 1 plus, if we're in size A, this is A minus 1, x2 lambda 2 plus A minus 2, and so on, all the way up to xa to the lambda A plus 0. So this is the same definition of Schur polynomials in the regular case, it's just now we're using odd divided difference operators. Right, so the same way which I could think of symmetric functions as being the cohomology ring of the full flag variety, and that having a basis given by all Schur polynomials, when I restrict to the cohomology of the Grassmannian, I'm just restricting to those Schur polynomials which fit in a box of the appropriate size. All of that's working in this non-commutative setting. I'll just point out, if you're kind of wondering exactly what these rings are like, it's very much like the Borel picture of cohomology for the Grassmannian, where you treat a certain parameter as being supercommutative. So if I take the relation 1 plus x1t plus x2t squared plus xa t to the a times 1 plus y1 t plus yn minus a. So normally if I wanted to talk about the cohomology of the Grassmannian of A planes in, whoops, that n should be a lambda. In lambda, so A planes inside C lambda, I could take the sort of tautological bundle over the A plane and its complement and use that to generate the cohomology ring. So this is a relation, this comes from the Whitney sum axiom for the Chern classes of those two bundles. So this is actually a presentation of the cohomology ring. This is the ordinary one, right? Where these xi's commute amongst themselves. In other words, the xi's satisfy the elementary the symmetric function relations. These things commute with each other, and the y's commute with each other. So if we want to define the ring HAN, or the odd cohomology, it's the same formula. It's generated by the x's and the y's, where the x's satisfy odd symmetric relations. And this is just those relations I wrote on the board earlier, the way in which, ordinary for symmetric functions, the EI's commute with each other. But in the odd, they commute with each other with this weird sign stuff showing up. So if the x's satisfy that and the y's satisfy that, and t is superdegree 1, so t's skew commute with the x's, then I can actually get the same, that you can prove that this is the same as this ring here. So what am I saying? I'm saying that there's some analog of this Borel picture of cohomology where you look at the Chern classes of these various bundles, but working in a non-commutative setting where t's are, even though t's are skew commuting, this ring is non-commutative. And that's because the defining relation for the symmetric between the x's was that weird one where they didn't actually commute. So there's some sort of analog of non-commutative, some sort of non-commutative theory which is governing these cohomology of these various varieties. You can do the same thing with partial flag varieties and get odd analogs of all of these different cohomologies. Okay, so let me just recap. The NilHecke algebra is connected by cyclotomic quotients to the cohomology of the Grassmannian. That connection allows us to categorify irreducible representations. The odd NilHecke algebra is also connected to some odd analog of the cohomology of Grassmannian, and using this relationship, it's also sort of obvious that it's going to categorify d lambda as well in the same exact way, but where now the thing playing the role of cohomology of a Grassmannian is a non-commutative ring. Okay, so we've now categorified U plus SL2 and its irreducible representations. What's next? Well, we should categorify tensor products, and for this we can just use Ben Webster's work. And I guess I won't bother writing this down, but so tensor products. There's a natural definition of rings which categorify tensor products by taking exactly the diagrammatic definition that Ben gave, but working in this skew commutative setting. So there's a natural candidate for rings categorifying tensor products. Analogous to Webster's work. And by taking exactly the same constructions as in Ben's work, there's a natural, or conjectural, I guess, link homology theory associated to the NilHecke algebra minus and its tensor products. So how does the knot invariance work? Well, first you categorify the tensor products of irreducibles, and then you define certain bimodule maps corresponding to, I associate categories that categorify tensor products to the endpoints of a tangle. So this is some category of modules, of projective modules, over tensor product rings. and you cook up, in the same way that Ben did, functors that correspond to any tangle between these. So this is a functor. And we conjecture that this natural link homology theory that one could define should be related to the odd Covenant homology in the same way that Ben's theory is related to the original Covenant homology. I think I'll stop there.
Are there any questions?
The evidence question is this only type A?
Yeah, that's a really good question. Right now, the answer is yes. So there's some sort of just very basic problem that arises, which is when you have vertices connected by an edge, let's do simply laced, I and j, there's some quadratic relationship between the crossing of the ij strand. And for degree reasons, this has to be a degree 2 relationship. So in other words, this has to be some combination of a dot here plus a dot here. But if you want, I guess the answer is if you want it to be non-trivial, there's a sort of, you could make it where the i's and the j's are sort of interacting on their own and not supercommuting with each other. But if you make it like a real sort of true theory, you could take a dot here. I guess this is a little bit of a convoluted explanation, but the idea is if you take a dot here, use this relation, you get a dot here and a dot here. If I slide this dot, which I know there has to be some sort of rule for sliding it, and I push it down to the bottom, I get, plus or minus something that looks like this. So no matter which way you fix the signs, you can show that if these things skew commute, then it's not going to work out. So the most naive categorification, where you have different strands interacting in a non-trivial way, it doesn't work. But you might say, well, maybe there's somehow the I strands supercommute amongst themselves, but commute with the J strands. It's possible, but then it's sort of like, it's just taking the original categorification and switching the SL2 parts to this odd. It's somehow not very much more exciting than switching the NilHecke algebra to the odd NilHecke algebra. And we're sort of still looking for a truly somehow odd theory for the whole quantum group.
Can you get the full U2SL2?
No, that's another project. That's actually underway. So in the same way that the NilHecke algebra was the basic building block in my original categorification of the whole quantum SL2, it looks like the same thing will work. And how did I do that construction was I let this thing act on cohomology rings of Grassmannians and use that to sort of build up the basic defining relations. And with Alex Ellis, we're doing the exact same thing using odd cohomology Grassmannians.
Are there any other questions? Thank the speaker again.